But before we get started with nonlinear optics, let's look at what we did in lecture number 13. So in lecture number 13, we essentially did the transition from classical coherence to quantum coherence, that is classical wave mechanics to quantum mechanics. And there we saw that the idea of the field in classical wave mechanics is quite analogous to the concept of pure state in quantum mechanics. Similarly, the correlation functions in classical wave mechanics, this is very similar, very analogous to the concept of mixed state within quantum mechanics. So if you take the example of this orbital angular momentum state, then we write a field in the angle basis. We can write a field in the angle basis in terms of the fields in the orbital angular momentum basis, and that's the representation, and where this represents a coherent sum if there is no randomness in the field. Similarly, in quantum mechanics, we can write this like a state in terms of this ket vector, and this ket vector is in terms of this orbital angular momentum ket vectors, and this represents again a coherent sum. But if there is a randomness in the system, then this becomes just a symbolic representation. And then in that case, one essentially works with the correlation function. The correlation function in the angle basis is defined as V star phi 1, V phi 2, and the ensemble average. And if we go by this expression for V phi, then this W phi 1 phi 2, that is a cross spectral density function in angle, can be represented like this. Now analogously in quantum mechanics, we write when there is randomness in the system, and this randomness is in addition to the intrinsic randomness that a quantum system already has. So when there is just the intrinsic randomness, we represent the state by in terms of a pure state, but when there is additional randomness, then we represent this state by a mixed state, and this is how it is represented in quantum mechanics. That is a psi outer product and then the ensemble average of that. And if we use this representation for psi, then that's how we represent. Now if we take the matrix element of this rho, this density matrix, then we see that this is alpha L1, alpha L2 star, that's ensemble average, and then we get this phi 1, L1, L2, phi 2. And this is essentially the angle representation of the orbital angular momentum mode, and then this phi 1 L1 is essentially e to the minus I L1 phi 1, and so this matrix element we can represent like this. So we see that the density matrix element and this cross correlation function, they are doing pretty much an analogous job. Okay, so we also looked at, we know that the expectation value of an operator for a pure state is given like this, where A is the operator and psi is the state. So the expectation value of the operator is psi A psi. But if it's a mixed state, then the expectation value is given by the average value of the expectation value, and this is the ensemble average, and this we showed last time that this is equal to the trace of rho times A. Okay, then in the classical mechanics we have the concept of intensity, but in quantum mechanics we don't have the concept of intensity. The analogous concept we have is the photon absorption probabilities, that one asks the question as to what is the probability that of detecting a photon at some location r at time t. So instead of asking what is the intensity in quantum mechanics, we ask what is the probability for detecting a photon at location r and at time t, and this we showed that it can actually be given by this expression. So of course this extra ensemble average is when the field is mixed, but just this the first expectation value when the field is pure, and E minus and E plus, these are the positive and negative and the positive frequency parts of the field. And of course just like here, we can represent this quantity also as trace of rho times this quantity. So this photon absorption probability, this is analogous to the concept of intensity. Similarly, we have correlation in quantum mechanics, and that is represented in terms of this G function G1. So this represents a correlation in the field between the field points at R1, T1, R2, T2, and is calculated like this. So I is the state, and E minus and E plus, these are the negative and positive frequency parts of the field at R1 T1 and R2 T2. So that this basically represents the correlation between the states of the field at R1 T1 R2 T2. Now in quantum mechanics, we can here we have asked this question as to what is the probability of detecting one photon. We can also again, so this ensemble average is just this trace of this quantity. This is pretty much the same as every time this is second ensemble average is trace of rho times whatever is the operator. So now in quantum mechanics, we can also ask this question as to what is the probability of detecting one photon at R1T1 and another photon, that is a second photon, at R2T2. We don't have an analogous question in classical wave mechanics. So this quantity is given by this E minus R1T1, E minus R2T2, E plus R1T1, E plus R2T2, and then this ensemble average. Again, we can write this as the rho density matrix times this is the operator. So once we now that we have two photons in the system, we can ask the coincidence probability. We can have now a 4-point correlation function. Just like for one photon we have 2-point correlation function, when we have two photons detection, one can have 4-point correlation function. And just like this, it is given by E minus R1T1, E minus R2T2, E plus R3T3, and E plus R4T4, and so on. Okay, so we will be using these quantity coincidence and 4-point correlation as we study 2-photon coherence and 2-photon interference. But before we do that, I want to get into at least one physical process that produces such field. And the one way of doing it to go to the nonlinear optics, that's where we can produce these 2-photon fields. Okay, so let's just first go through the very basics of nonlinear optics. So first of all, the Maxwell's equation inside a medium is given by these 4 equations, where E is the electric field and D is the electric displacement sensor. These two are related by this expression, where D is epsilon naught E plus P, epsilon naught is the vacuum permittivity, and P is called the polarization. Polarization is dipole moment per unit volume. So what is dipole moment and what is polarization? So in an external electric field, if we have an atom, the positive core of the atom and the center of the negatively charged electron cloud, they are pretty much at the same location. So there is no relative displacement between the center of the negatively charged electron cloud and the positively charged nucleus. But if we apply an external electric field, then of course the negatively charged electron cloud will be pulled towards the field and the positively charged can get pushed away. And as a result, the center of the negatively charged electron cloud won't be at the same location as that of the positively charged nucleus. And so there will be some separation between the two. So let's say that separation is D. Now, since what we have here is this two charges separated by distance D, and so that introduces an effective dipole moment. And so this is for one atom, and once we calculate the dipole moment per unit volume, that is what gives us the polarization. So what happens when we have this polarization? So let's look at it one by one. So in the case of vacuum, that is when there is no medium, we have just the electric field, and then of course the polarization is 0 because there is nothing, no medium to get polarized, and in that case D is simply epsilon naught E, just proportional to E. But when there is a medium, that is a linear medium, and a linear medium is essentially defined by that when the applied field strength is not very strong, then every medium just behaves as a linear medium. And what that means is that when we have an external electric field which is not so strong and there is a medium, then of course this electron cloud gets displaced from the nucleus by distance D, but and of course there is a restoring force from the charges, and this restoring force is simply proportional to the displacement D. So this polarization is basically proportional to the electric field, that is P is epsilon naught chi 1 E. So when the applied field is not very strong, this displacement and hence the polarization is just proportional to the applied electric field, and this chi 1 is called the linear susceptibility. And in this case, the displacement is given by, which is epsilon naught E plus P, now that we can write as epsilon naught E plus epsilon naught chi 1 E. So this chi 1 is the linear susceptibility. Now in the case of nonlinear medium, which essentially means that the applied field strength is very strong, then this electron cloud gets displaced from the positively charged nucleus by a much larger amount than when the field was not so strong. And as a result, the restoring force on the electron is no longer just proportional to the displacement D, but it is also proportional to the D square and so on. And as a result, the polarization is which was earlier just proportional to D and hence E, now this polarization is also proportional to E square and E cubed and so on. These terms we can also write as P1, P2, P3. P1 is the linear polarization, P2 is the second order nonlinear polarization, P3 is the third order nonlinear polarization, and so on. Chi1 is the susceptibility, Chi2 is the second order susceptibility, and Chi3 is the third order susceptibility, and so on. This we can also write as this is the P1 is the linear, and then this P2, P3, and so on, that we can also that we can write as the non-linear polarization. So if this is the polarization, the electric displacement vector, that can be written as d equal to epsilon naught E plus P, and so that's epsilon naught E and epsilon naught chi1 E, that's the first term, second, third, and so on. And the chi2, chi3, these are the second order and third order susceptibility, and so on. So whether a medium behaves as a non-linear medium or linear medium all depends on the applied electric field. So the field is strong enough, then the medium will start behaving as a non-linear medium. It also of course depends on what is the strength of chi2 and chi3, that is these higher order susceptibilities. So a medium having very high chi2 will start behaving as a nonlinear medium at a much lower field than a medium that doesn't have that high chi2. So this is how we get this is how the polarization becomes dependent on the second order and third order in the field. Okay, so this was about how the polarization gets introduced. Now, since we are talking about fields, we also need to talk about how the field propagates inside the nonlinear medium. So let's take a simplistic, the most simple situation, that's rho equal to 0, j equal to 0, and the material is magnetically isotropic, that is B equal to mu naught H. Now in this case, that's the set of Maxwell's equation. And now here we can take up this one and we can write this as del cross E. I'm just taking the del cross on each side. So this mu naught del by del T, and then we have del cross H. Now this del cross H is del D del T. So this becomes minus mu naught del square del T square D. And so this is D, we know that is epsilon naught E plus P. So we can just rewrite it like this. This del cross E, we can use a vector identity and we can write it as del dot E minus del square E plus mu naught epsilon naught, this we are putting together, mu naught epsilon naught and then E, and then we put this term on this side. And so what remains on this side is minus mu naught del 2P by del T2. So just rewriting it. Now we know that this del dot E is 0 for linear optics, but for nonlinear optics it is actually not 0, but it is negligible. So without actually going into the details of how this comes out, for the details one can actually look at this. This is a very nice book on nonlinear optics by Robert Boyd. This is a third edition as well for this. So for the kind of intensities we would be interested even within nonlinear optics, this del dot E is 0, and therefore we can write this one as just del 2E, and now since we can change the signs here, this becomes minus 1 over c square del 2E by del T2 plus mu naught del 2P by del T2. So this is the wave equation inside a nonlinear medium. And of course, when P is equal to 0, we get the vacuum equation. So this del 2E minus 1 over c square del 2E by del T2 equal to 0. That is a regular wave equation that we are all familiar with. So but when it's inside a medium which has a polarization, that is the wave equation. Okay, so this is the wave equation inside a nonlinear medium. We just want to write it in a slightly different manner as well. So let's see how we can do that. So we can write this polarization, that's the total polarization inside the nonlinear medium, as the linear part and the nonlinear part. This nonlinear part will have the second order, third order, and all the higher order terms. So we can just simply write as the linear part and the nonlinear part. We can then write this one as the left hand side remains as it is, and the right hand side we can write as mu naught del 2 P1 P nonlinear by del T2. This P1 we are bringing onto this side, so this 1 over c square. So we have E from here, and then P1 by epsilon naught from there. So here we have used that this E naught, the relation between E naught, epsilon naught, mu naught, and c square. So and this mu naught del 2 by del T2 P and L, that remains on this side. This P1 we know that is equal to epsilon naught chi1 E. So that's how we write it, and that's how the epsilon naught gets cancelled. So that's what we get on this side. This E plus chi1 E, that's 1 plus chi1. That 1 plus chi1 is equal to n squared. and that n is the refractive index of the medium. So this then we can write as del 2 E minus n square by c square del 2 E by del T2, and that is equal to mu naught del 2 by del T2 P NL. So that is the wave equation inside the nonlinear medium, and where n is the refractive index of the medium. So of course, with the total polarization is 0, we just get the vacuum equation. If we are in the linear optics regime, that means we only have the first order polarization, then the wave equation we have is del 2 E minus n square by c square del 2 E by del 2 equal to 0. But when we go into the nonlinear optical regime, then that is the wave equation that one has to follow. So this contains all the nonlinear optical terms. So that's the wave equation inside the nonlinear medium, and depending on whether we are looking at the second order effect or third order effect, we will have the appropriate expression for P nonlinear over here. Okay, so now let's look at some very basic second order nonlinear optical effect, and the sum and frequency generation are some of the very basics. So now we'll work just with the scalar field, let's say the real scalar electric field, and let's say it just consists of two different frequencies. So this is just a scalar field and of two monochromatic frequencies. So Et is E1 e to the minus I omega 1 t plus E2 e to the minus I omega 2 t. We are also taking the complex conjugate parts. So if this is the electric field, and if we have a medium that has the second order polarization, then the second order polarization we know that is given by epsilon naught chi 2 E square t. And so if we write it for this field, what we see is that epsilon naught chi 2, and then we have this epsilon naught E1 minus I omega t plus E2 E minus I omega 2 t, and this is the complex conjugate part, and then the square of that. So if we expand it, of course we'll get 16 terms. So I'm writing it one by one. So these are the 16 terms. So first of all, we collect terms that without any time dependence, and that we will have E1 star plus E2 star. So and there's a 2 here, so there's four terms here. Then all the other terms will have this epsilon naught chi 2 here, and then we have 2 here, 2 here, and 2 here, so that's 6, and the 6 complex conjugate parts, so 6 plus 6 is 12 plus 4 here, so that's a total of 16 terms when we expand it. So these do not have any frequency dependence, but these terms do have frequency dependence. So now let's look at these terms. Again, we need to see here that the incoming electric field, the applied electric field, had only two frequencies, omega 1 and omega 2. But the polarization that got induced inside the medium, that contains newer frequencies as well. For example, now here we have, in these terms, we have 2 omega 1, 2 omega 2. So although the incoming field had only omega 1, that actually through second order nonlinear effect, it actually generates field at 2 omega 1 and 2 omega 2, and this is called second harmonic generation. So it's like if we come in with a red light, then we can actually generate blue from there. So that's the second harmonic generation. Now this term represents the sum frequency generation, because we had omega 1, omega 2, but now we have a field that has a frequency omega 1 plus omega 2. Similarly, we have difference frequency generation, that means we have a field that has frequency omega 1 minus omega 2. So although we had just omega 1 and omega 2, but just because the medium has the second order nonlinear susceptibility, and as a result second order polarization, we can produce all these different fields that are at twice the frequency, the field that are the sum of the frequencies, and the field that is at the difference frequency as well. Okay, so this is the second order nonlinear effect. This is a very basic, and this is what we get when we have just two monochromatic frequencies in the incoming field. Now, what are the ways in which such fields can actually be generated? For example, I just want to look at the difference frequency generation and what are the schemes by which it can be done. So this is one scheme. For example, we have a nonlinear medium that has chi 2, that is a second order susceptibility. Now if we come in with two fields, just like what we did in this example, that we come in with the field that has two frequencies omega 1 and omega 2, then we can actually produce a field omega 3, which is at omega 1 minus omega 2, that is the difference frequency. But of course, here we have the two fields are present, so it's very efficient, but we can also do this frequency, difference frequency generation in such a scheme where we come in with just a monochromatic field omega 1. But since in quantum mechanics, within field quantization, we have the concept of vacuum modes. So all the vacuum modes are actually present. That means the vacuum modes at omega 2 and omega 3, all the frequencies, actually the vacuum mode is present. So here, because of chi2, there is a finite probability that we can generate fields at omega 2 and as well as fields at omega 1 minus omega 2. This omega could be anything. This omega 3 can be anything as well, except that this omega 3 has to have this relation that omega 3 is equal to omega 1 minus omega 2 in order to conserve energy. So in order to generate this difference frequency, we need not have two fields. If we do have two fields, then it's very efficient. But even if just one field is present, we can still generate field at this difference frequency omega 1 minus omega 2, and of course this process will actually be very inefficient. So in an actual atomic system, we will have that the atom absorbs this field at omega 1 and in turn emits two fields, one at omega 2 and other one at omega 3. Of course, it could be any omega 2, but omega 3 has to have this relation that it is equal to omega 1 minus omega 2. And in fact, such a process is actually called parametric down conversion. So although it is as simple as this difference frequency generation, what we have here is that a medium absorbs one photon and emits two different photons at frequency omega 2 and omega 3, and they have a relation like this. So this parametric down conversion, this refers to the fact that the energy remains conserved during the process. And there are non-parametric processes as well, which are non-energy conserving. But we want to be studying this parametric down conversion in detail because this is one process that through difference frequency generation scheme, it actually produces a two photon field. That means here the system takes in one photon and these then emits two photons. So that's a two photon state. And later we find that this two photon state is also represents a two photon entangled state that we will do after. That aspect of this field we'll look at in detail after a few lectures. But right now we just want to use what's produced by parametric down conversion as an example of a two photon field, and through that we want to study how two photon coherence, two photon interference, and these effects, how it all actually works. So we will stop here. Thank you.